Hi, welcome back to Calculus. Today we are looking at section 3.2, the derivative as a function. So we started looking at derivatives in section 3.1. We had a definition, but we had the definition for the derivative at just one point of a function, or one point of a graph. And so we're going to expand that just a little bit and make it into its own function. So here we go. The derivative of a function f of x with respect to the variable x is the function f prime, or f prime of x, whose value at x is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, or another similar definition, f prime of x is equal to the limit as z approaches x of f of z minus f of x all over z minus x. Okay, so a lot to unpack here. Basically, this first part should look really similar. The difference is, in the last section we did it with an a. We had a very specific value for x that we were working with, and so we were able to get numbers out of it. Here we're not going to be able to do that. We're not going to be able to get a number because we're going to still have the variable x running around, and that's fine. It's going to work just great. It just will be a function then that we could use, and then we could find the derivative at any point that we wanted for that function. We wouldn't have to run through this every single time we wanted, to know the derivative at a different point. We'd have a function to give us the derivative for anywhere we could want. And we do have this secondary little bit of a definition. The limit as z goes to x. Basically, if you remember our pictures from the last section, we're dragging those 2 points together to try and get a slope that becomes the slope at just one point. And so that's all that's happening here. We have a slope equation in here, f of y2 minus y1 over y2 minus y1 over x2 minus x1, where that z is that second point. We're just dragging it closer. So this one comes in handy occasionally. Most of the time we're going to work with that first one. So we're going to need a little bit of notation, then we're going to do some examples, and yeah, well, actually there's a lot of notation in this section, so just kind of buckle up and we'll have some fun. All right, let's get another board. Okay, so not a whole lot on this particular board, just some notation. These all mean the same thing. These all mean to take the derivative with respect to x. So we have the derivative with respect to x of a function f of x. That just means take its derivative. We have the notation f prime of x, which we saw in the definition just a minute ago. We can use y prime. Sometimes we have equations that have y equal to something. It's really the same thing, right? Y and f of x, they're kind of, sort of, almost interchangeable, but not quite. So we can talk about having y prime as a derivative instead. And to go along with that, we can have the derivative of the function y, or the equation y with respect to x. We can have the derivative of the function f with respect to x. And then these last two are really kind of unusual. They don't happen a whole lot. I'll be honest, I haven't seen them very many times for myself. Big capital D with f of x on the inside, that means take its derivative. And d with a little x is the derivative with respect to x of f of x. Now, one little piece of information here, that with respect to x that we keep talking about, obviously we could have a different variable. We could be working with t instead, and then we'd be having the derivative with respect to t of f of t. That seems relatively straightforward to swap in a different variable. But the big reason we have this with respect to x bit is because at some point we're going to do some crazy stuff. We might have more than one variable running around and we only want a derivative with respect to one of them. Okay, so that's coming later. It's something to think about. We have multivariable functions. And this, so just keep in mind that with respect to x is just telling us this is the only thing I'm considering to be a variable, which is kind of fun and weird to think about. All right, so now we're going to move in and we're going to do, looks like I just have really one example of finding a derivative. Because a lot of this is very similar to what you did in the last section. We're just going to have functions now that come out instead of individual slopes. So let me get a new board. All right, so now we're going to find a derivative function. All right, we're going to find a derivative of an entire function. Last section, like I said, we did this at a single point. Now we're doing it for the whole thing all at once. And we're going to keep this example, we're going to use some of this example on the next board as well. So make sure you get this all written down so that you have it ready to use when we move on. All right, so I want to find the derivative with respect to x of the function 1 over x minus 3. All right, nice little function. So we set up our limit. F prime of x is equal to the limit as h goes to 0 of 1 over, now remember this is f of x plus h, so I get an x plus h in here in place of that x. So 1 over x plus h minus 3 minus f of x, the 1 over x minus 3, all over h. So I have two fractions here. The big problem is I don't like that h in the denominator. We just need to clean this up and it's going to work out just fine for us. So I start by getting a common denominator. My common denominator is x plus h minus 3 times x minus 3. You can see I actually wrote it the other way. But so the first fraction has to be multiplied top and bottom by x minus 3. Gives me x minus 3 over that mess. And the second fraction has to get multiplied by x plus h minus 3. So again, you can see I get x plus h minus 3 over the messy denominator. All right. So we did that, we got a common denominator, which means we can put these two fractions together. And yeah, this is an h. I know it looks probably like an n, but it is an h. There we go. That's a little bit better. So what's fun here is a couple of things. First, when I put these together, notice I have x, but then I have a minus x over here. So the x's go away. I also have a minus 3, but then a minus 3. So the only thing that's really left is the h. Okay, if you need to, throw this in parentheses and work out that subtraction for yourself. But I promise, the only thing left on the top of this when we put these two fractions together is the h. The other important thing is that this h on the bottom, remember, dividing by something is the same as multiplying by 1 over that. So I was able to include this h then in the denominator, because remember, dividing by h would be the same as multiplying top and bottom, by multiplying this fraction by 1 over h. So I'm able to bring this h into the bottom of the fraction, which is nice because now I have h on the top and h on the bottom. Those go away, leaving me with 1 over x minus 3 times x plus h minus 3. Now this is still a mess, but the important thing is now 0 could be plugged into this limit, right? 0 is not a problem anymore. If I put 0 in here for h, I'm not going to get 0 in the denominator, right? If I put it in here, 0 times anything is 0, it still blows up. But as soon as I get rid of those h's, now I can plug it in. And when I do that, I get x minus 3. This h is gone, so I get x minus 3 again. I just get the function then 1 over x minus 3 squared. And that is, we started with it way back there, but I'll write it down again. That's my f prime of x. There's my derivative function for x, for this function. All right, that was fun. So hang on to this answer, okay? That's specifically what we're going to need. I'm going to use that again on the next board for a little bit more work. So let's keep going. All right, so I have my derivative function written down here again. F prime of x is 1 over x minus 3 squared. I just want to find the tangent line for my original function, which was 1 over x minus 3, which I should have written on the board, at x equals 4. So now we're just going to take advantage of this derivative that we just found to find first the slope and then the equation of the tangent line. So the slope is equal to f prime of 4. Right, that's what we said the derivative was, is the derivative at a point was the slope of that curve. So we just have to plug 4 into our derivative. So you can see where having the derivative as a function is pretty useful because we can find any values for this slope that we want, anywhere we want. We just have to plug in the number. So we plug in 4, I get 1 over 4 minus 3 squared, again plugging it in here. Work it out, you get 1. So there's our slope for the tangent line. We do, however, need one more thing for the tangent line. We need a y value for this point. Right? We have the x value. We're working with 4, but we need to know the y value so we can write the tangent line. So if we just plug 4 into the original function, 1 over 4 minus 3 gives us another 1. So the tangent line in point slope form is y minus the y coordinate of 1 is equal to my slope times x minus the x value of 4. And there we go. There's our equation for the tangent, for this tangent line. So let's go ahead and get another board and talk about some more fun stuff. Okay, continuing on. We have a little bit more notation, then we're going to talk a little bit about some graphs, and eventually where derivatives don't exist. So, some notation for x is equal to a. So now, notation for derivatives at a point. We kind of talked about this a little bit in the last section, f prime of a, right? We have derivatives at a specific x value, but we could also write that as dy dx, and then this line here just means evaluated at x equal to a, or the derivative of f with respect to x evaluated at x equals a, or the derivative with respect to x of f of x evaluated at x equals a. So that's some more notation that you might see. Let's talk about graphs. Derivatives can be graphed just like any other function, right? We just did a derivative and we got a derivative function. We could have graphed that. Whenever f prime of x is greater than 0, that means that the original function f is increasing. Remember, the derivative gives us the slope at a point. So if you have a derivative that's positive, that means the original function had a positive slope. It's going uphill. Does that mean that the original function is also positive? No. The function could be negative, but going uphill. That's not, that's pretty easy to draw. Draw a parabola that goes underneath the x-axis, and for part of it, it's going up, but it's underneath the x-axis, so it's got a negative value. And similarly, when f prime of x is less than 0, that means that the original function f is decreasing. Again, it doesn't mean that that the original function is negative. It just means that the original function was going down. All right, one more board and we should be all set. All right, here we go, last board. Where is there no derivative? So we have 4 places on a graph or for a function where we would have no derivative. First one is if you have a corner. Long story short, remember the derivative is the slope. So what happens is, as you come, in this example, as you come in from the left, you have a positive slope, but if you were coming in from the right, you'd be looking at a negative slope. Those the limits there on either side are different, meaning that the limit at that point doesn't exist. So if you have a corner, no derivative. No limit, no derivative. At a cusp. A cusp is when one or both sides actually have limits that are infinity for those slopes. And as we can see, it doesn't even matter that they're different. Just the fact that either one of them is infinite ruins the derivative. It means you don't have a slope at that point, right up here. If you have a vertical tangent, so in this case, my graph comes and it's pretty flat, and then it dives down and then levels, and then turns back. But the important part is right in here. Right in the middle here, there is going to be a spot where just for an instant, this thing has a vertical tangent line. Since the derivative is the slope of the graph at a point, and the slope is undefined, that means the derivative is undefined, so it doesn't exist. And last but not least, I didn't draw any pictures, but anytime you have a discontinuity, if you have a jump or an asymptote, any of those things, that's going to ruin your ability to take a derivative at that point. Last point here is that if you do have a function that's differentiable at a point, or everywhere, that implies then that it is continuous either at the point or everywhere. That does not work the other way around. If you have a continuous function, it is not necessarily differentiable. Case in point, all 3 of these would be continuous functions, but they're not differentiable. The limit of that difference quotient does not exist for any of these 3. So there you go. That's the limit as a function, or not the limit, sorry, the derivative as a function. There we go. Have a wonderful day. Bye.